Good morning and happy Wednesday. Today we are going to do our introduction to a new topic, and I'd like you to guess what that topic is based on the 4 images you see above. These 4 images have something in common. The singers in High School Musical, the act of singing, has something in common with light, which has something in common with a microwave, which has something in common with the machine that produces ultrasound images. All 4 of these things involve waves. So today is our introduction to waves. What is a wave? A wave is a disturbance that travels through a medium from one location to another. And if we were in class right now, we would be using slinkies to visualize waves. There is an image of a slinky below, and there's a disturbance traveling from the left side to the right side of the slinky. A wave transports energy, not matter. So the matter is moving in place over and over again, vibrating in place, and the energy is moving forward in some direction. So in the slinky, the particles are moving, vibrating left, right, left, right, left, right, but in place, in the same spot. And overall, there's a movement from left to right, and that's the energy that's moving, not the matter. In the image below that, the people going up and down to create a stadium wave, they're also not moving left to right. The wave overall is moving left to right, and that's the energy that's moving. The matter, the people, are just vibrating in place, up, down, over and over again. Do waves move? We kind of just addressed that. So the energy moves from place to place, but the particles do not. The particles just move back and forth. They vibrate back and forth. So we have 2 types of waves, and you've actually just seen an example of both types. You have longitudinal waves and transverse waves. A longitudinal wave is a wave in which the particles move back and forth in the same direction as the wave. And a transverse wave is a wave in which the particles move back and forth at right angles to the direction of the wave, perpendicular to the direction of the wave. So if you're looking at this image down here, the one at the top, someone is jolting the slinky back and forth, and the slinky is vibrating left, right, left, right, left, right. This is parallel to the direction of the wave. The direction of the wave is left to right, so the upper image is a longitudinal wave. The lower image, the person is vibrating the slinky up and down, but the wave itself is moving left to right. Therefore, the slinky particles are moving back and forth at a right angle to the direction of the wave. So the lower image is an example of a transverse wave. The human wave that we saw earlier is an example of a transverse wave because the humans are moving up and down, and that is perpendicular or at a 90-degree angle to the direction of the wave, which is left to right. So we're going to talk about wavelength, frequency, and wave speed and how those 3 things relate to each other. The wavelength is the distance between 2 consecutive crests of waves. The crest of a wave is the topmost point, and if you find 2 points of a wave that are at the highest point, that come one after another, and measure the distance between those 2, that's the wavelength. So for example, on this wave we see below, one crest is here on my cursor. The other crest is where my cursor is now. The wavelength is the distance between these 2 crests. And we typically measure wavelength in meters. Frequency is how many waves go past a point in 1 second. And it's measured in something called hertz. Hz. The unit hertz is an inverse second, so we also see it represented as seconds to the -1 power or 1 over seconds. The higher the frequency, the more energy the wave has. So as frequency increases, the energy of the wave increases. In the images to the right, the one at the top has a higher frequency and a shorter wavelength. The one at the bottom has a lower frequency and a longer wavelength. As frequency increases, wavelength decreases. As frequency decreases, wavelength increases. So they have what we call an inverse relationship. We can calculate the speed of a wave by taking frequency multiplied by wavelength. So if we're using letters to represent these variables, speed of wave would be represented by V, frequency would be represented by F, and wavelength is represented by this symbol that looks like an upside down Y. Wave speed is measured in meters per second. Frequency is measured in hertz, which is an inverse second, and wavelength is measured in meters. We are now going to do some examples finding speed, frequency, and wavelength. Example 1 involves finding speed of a wave. The question is, what is the speed of a wave that has a wavelength of 3 meters and frequency of 2 hertz? Step 1 is to define the variables, so we want to pick out the numbers and decide what they represent in the equation. So the first number we see is 3 meters. Since it's followed by m, meters, we know this stands for wavelength. So wavelength equals 3m. The next number is 2 hertz. Hertz is a unit of frequency, so we know frequency equals 2. And then finally, we need to know what we're looking for. And the question asks you to find speed. So speed equals question mark. Step 2 is to write out our equation. Our equation is speed equals frequency times wavelength. Step 3 is to plug in our numbers and solve. So if speed equals frequency times wavelength would be 2 times 3. 2 times 3 is 6, and speed is measured in meters per second. Example 2, we're going to find frequency. What is the frequency of a wave that's traveling at a speed of 2 meters per second and has a wavelength of 4 meters? Step 1 is to define the variables. So our first number is 2 meters per second. We know that's speed because it's measured in meters per second, and speed is typically measured in that unit. The next number that we pick out is 4 meters. 4 meters is wavelength because we know meters is a unit of wavelength. And then finally, what we're looking for is frequency. So frequency equals question mark. Step 2 is to write out the equation. Our starting equation is speed equals frequency times wavelength, but we're looking for frequency. So we need frequency to be by itself on one side of the equal sign. To do that, we need to get rid of wavelength on the right side of the equal sign. We can do that by dividing both sides of the equation, both sides of the equal sign, by wavelength. Wavelength divided by wavelength is 1. So on the right side of the equal sign, we're left with frequency. On the left side, we're left with speed divided by wavelength. So frequency equals speed divided by wavelength. Step 3 is to plug in the numbers and solve. So our numbers were 2 for speed and 4 for wavelength. If frequency equals 2 divided by 4, then it's 0.5 or 1/2 hertz. Example 3, finding the wavelength. Our problem is, what is the wavelength of a wave that has a frequency of 5 hertz and travels at a speed of 10 meters per second? Step 1 is to define the variables, pick out those numbers, and tell us what they represent. So the first number is 5. Because it's measured in hertz, we know it's a unit of frequency, so we write frequency equals 5 Hz. 2, speed. The next number we see is 10 meters per second. Meters per second is a unit of speed, so we're going to say speed equals 10 m-s. And then finally, we're looking for wavelength, so we're going to write wavelength equals question mark. Step 2 is to write the equation. Again, our starting equation was speed equals frequency times wavelength. But we're looking for wavelength, so we need wavelength by itself on one side of the equal sign. We're going to divide both sides of the equation by frequency. So on the right side of the equation, frequency divided by frequency is 1, and now it disappears. So we're left with wavelength equals speed divided by frequency. So to find wavelength, all we need to do is plug in speed and frequency. So if wavelength equals speed divided by frequency, it is 10 divided by 5, which is 2 meters. Now you're going to do some problems of your own. And before you start, I just want to emphasize that waves are really, really important to our everyday lives. Cell phones, which you use every day, use radio waves to transmit your voice when you're talking on it. So without waves, the modern technologies that we use wouldn't be possible. So it's very important for our scientists and engineers to understand how waves work and how to use them to create the resources we use every day to help advance communication and medicine and all kinds of things that improve the human condition. So thank you for listening. You guys are fantastic. Keep up the good work. I'm so proud of you.